For over a century, Albert Einstein's general relativity has stood as the standard for predicting gravitational phenomena. This equation defines the mathematical mechanism of the theory. On the right, the energy-momentum tensor represents mass. On the left, the metric tensor dictates how that mass curves a four-dimensional spacetime continuum. However, this formulation presents an ontological difficulty. The metric tensor describes the curvature of an entirely empty, non-physical void. During gravitational collapse, spacetime can compress into an infinite, dimensionless point. This creates a singularity where known physics ceases to function. General relativity functions as a predictive geometric model, but it lacks a substantive medium to explain the physical origin of gravity and inertia. In 2026, Menelaos Georgiadis published a paper proposing the Elastic Continuum Theory as a mechanical alternative to the concept of empty spacetime. This new theory treats the vacuum of space as a dense, hyperelastic solid lattice known as the plenum. By introducing a physical medium, the study of gravity moves from the realm of pure Riemannian geometry into the domain of continuum mechanics. In this framework, gravitational attraction is a deterministic acoustic and optical refraction occurring within the solid lattice. To see how a solid-state structure can replicate the effects of spacetime geometry, we must examine the mechanics of the plenum from first principles. This is the unperturbed state of the solid plenum. It is a uniform, flat, three-dimensional mechanical lattice representing the flat Minkowski background. Every point in this lattice is governed by the elastic displacement field vector, u-mu, which tracks how any part of the medium is mechanically shifted. Defining the vacuum as a solid changes how we define matter itself. Matter exists as topological solitons, localized, self-sustaining wave packets of energy. As these solitons move, they stretch and compress the displacement vectors of the surrounding lattice. This displacement creates immediate mechanical changes in the medium. The presence of a soliton alters both the local density and the shear modulus of the elastic lattice. Mass is the active topological strain state of the solid vacuum itself, rather than an object residing within it. This equation governs how lattice strain affects wave propagation. C0 is the unperturbed wave velocity of the plenum, alpha is the coupling coefficient, and C local is the local phase velocity. As lattice displacement increases near a mass, local wave velocity decreases. Now imagine a secondary wavefront or a smaller soliton approaching this region of altered density. Basic wave mechanics dictate how waves behave when moving through a medium with a variable refractive index. The advancing wavefront naturally curves toward the region of lower local wave velocity, creating a path that mimics an orbit. Under this model, what appears to be freefall along curved geodesics is a result of deterministic acoustic refraction through the medium. The Georgiadis master equation provides the mathematical bridge between continuum mechanics and non-Euclidean geometry. On the right side, the equation starts with the flat Minkowski background. The elastic moduli tensor and mechanical strain gradients modify that baseline to produce the effective acoustic metric on the left. This metric is the field experienced by any wave or soliton propagating through the strained plenum. The observed curvature is a result of physical strain gradients within the lattice, rather than a deformation of geometry itself. This allows Einstein's field equations to be recovered as an effective field theory of a stressed elastic solid. This mechanical framework addresses the problem of infinite singularities that occur in standard general relativity. We can apply the same gravitational collapse scenario to the elastic continuum model. Because the plenum is a physical solid, it has finite physical limits for compressibility and shear stress. As solitons compress inward, the elastic moduli dictate a maximum possible strain. The lattice reaches maximum compression and locks, preventing a dimensionless point. Within this theory, infinite singularities are mathematically prohibited because a physical solid cannot be infinitely compressed. General relativity transformed physics by providing a predictive geometric framework for the universe. Elastic continuum theory preserves that predictive power while providing a foundation in physical reality. Mass strains the hyperelastic medium of the plenum. This mechanical strain creates the phase velocity gradients we observe as gravity. Treating the universe as a hyperelastic plenum removes infinite physical paradoxes and provides a deterministic mechanical cause for the behavior of gravity.